All right, so here's a continuation of the volumes of solids of revolution. We're talking today about rotating the area that we are able to uncover here or discover between two curves. Instead of rotating it vertically around the x-axis or around a y-equals line, we're going to explore what it looks like to rotate it around the y-axis or the x equals a certain line. So we're basically doing the inverse of what we've done. Before, what we've done was we've taken, the volume has been the integral from 0, which is like, or from an x point, from x1 to x2 of f of x dx, right? So this is rotating some kind of area vertically, okay? Like this, up, down, up, down. Now what we're doing is we're actually doing this. We're finding out the volume. We're going to integrate from y1 to y2, okay? Everything's inverse. And we're going to do f of y dy. So we're going to use the same process, but we're going to have to invert everything, really, okay? So we go the opposite way or perpendicular, whatever. So let's just highlight a few things from this notes package here. When we want to rotate about the y-axis, then the axis of rotation, if it's the y or if it's something parallel to the y-axis like x equals something, right? Like if it's x equals something, then the integrand, so the integrand needs to be in terms of y. And that's what I had highlighted out here, okay? So up here, normally we have y equals something, something, something involved with x, something, something, x, whatever, right? Well, here, this is going to be x equals something, 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 y equals something, something, y, whatever. So we need to isolate for x here, right? Everything is opposite. Everything's opposite. And the limits of integration, as I mentioned, the limits, the lower limit and the upper limit, need to be y values. So we are now looking for, guess what? We're going from here to here. So the integral is from here to here. Okay, if you can kind of imagine that. And before, let me go back to a previous example here. Before, the limits of integration were here to here, right? Here's the integral, there to there. Okay, everything's in terms of, y in terms of x. Okay, so we're going to change that now. We're going the other way. Integral is going to be y now. What else do we need to know? Find the points of the intersection of the curves from the being rotated points of intersection of the curves that form the region. Okay, so we're going to use the y values of these points of intersection now. Okay, so consider the region pictured to the right that's bounded by the graphs y equal. Okay, now they're giving us in y because most functions are given in y. We're going to have to change that around, so watch carefully. But we've got y equals plus or minus the square root of x, so that would be, here's positive root x. Here's minus root x or negative root x, okay? And y equals x plus 2. So here's x plus 2. So find the volume when the region is rotated about the y-axis. Okay, so when it's rotated sideways, I need to flip everything around. First thing we're going to do is we're going to write these functions, okay, of x in terms of functions in terms of y. Okay? So I'm just going to get my notes here. Okay. So what we're going to do is we're going to square both sides of this first one, and we're going to have x equals y squared. Okay, x equals y squared. That's supposed to be a 2. And we're also going to isolate for x, so this is going to be x equals y plus 2. Everyone see that? Okay, you guys okay with that? That's the first thing we need to do if we're going to integrate this opposite way. Everything is inverted. Okay, everything's inverted. Everything's switched around. Y is here, f of y, dy, all that. Okay, so we're going to do that, and we're going to envision the axis of symmetry as a vertical line instead, okay? And the rules still hold true with what we learned before, okay? So we're going to use the function that's the farthest away from the axis of rotation. In that case, the one that's farthest away is going to be this x equals y plus 2. And the one that's closest is going to be this x equals y squared. All right, is everyone okay with that? So to find the rotation, so here's what we do. The volume of this solid when it's rotated this way is going to be, and we got to do pi r squared, right? Pi r squared. The r is just going to be the difference between these two functions in terms of the x and functions. So it's going to be pi still. We're going to have an integral still. We're going to go from the y values of -1. Maybe I'll zoom in so you can see that a bit better. We're going to use the y values of -1 right here. -1 to +2. So we've got -1 to 2, okay, in the y direction there. All right, so here we go. So we've got the y minus 2, or sorry, y plus 2 minus the axis that we're rotating around, which is x equals 0. Okay, so the y-axis is actually x equals 0. We're going to square that minus y squared minus 0 squared dy. Don't forget your dx, dy, and all that stuff, you know, when you're doing your integrals, okay? Okay, you good with that so far? We flipped everything around. We got some thumbs up here. All right. Okay, so now the rules of integration and stuff, they're all the same. We just have to consider, you know, y is the same as x here. So we do everything the same. Should we combine this? Yeah, probably could help ourselves there. So let's just rewrite some of the stuff. Okay, y plus 2 squared minus y squared. So that's going to be, what's that going to be? Y squared plus 4y plus 4 minus y squared dy. Okay. Nope. No, that's y to the 4th. My bad. Y to the 4th. Did that yesterday too, I think. So we're going to integrate this now. And again, this would be a question on the AP exam where you wouldn't have a calculator allowed. So we're going to do this manually. Luckily, we can do this manually. So we're going to have pi times, okay. So the integral of y squared is y cubed over 3. This is going to be 4 over 2y squared. This is going to be 4y. This is going to be y to the 5th over 5. And we're going to evaluate this from -1 to 2, our limits of integration. Everybody's good there so far? Okay, so you know what to do here now. I'm going to save this pi just for really later here. Okay, so I've got 2 cubed over 3, which is 8 over 3. 4 over 2 is 2 times 2 squared. 2 times 4 is 8. Plus 8 minus 32 over 5. And I'm going to subtract in there this stuff evaluated at -1. So that's going to be -1/3. This is going to be plus 2. 2 times -1 squared, which is just 2. And then it's going to be minus 4. And -1 to the 5th is a negative, so it's going to be a plus 1/5. Okay, just shout out something if you think I'm making a mistake here. It's quite possible with this little addition here, so I'm going to try and keep going. We're going to get everything, try and subtract everything, get over the same denominator. I might just spare you in the video here, so I'll pause and I'll just do this in the background. All right, so here's the answer when you do all this. Again, you're going to have to just use paper and pen. On a question like this in the AP exam, probably not going to have a calculator at all. So common denominator, add up, simplify what you can. So 72 over 5. So the bottom line is here, what's new is that this is still a volume. It's still an integral, pi times whatever squared. You're going to have to take the outside function, which of course is going to be the function that's furthest away from the axis of rotation, when all this is in terms of x in terms of y, and so on, and add them up. Okay? Now, what about if we did the same thing, except we want to find the volume for the region when it's rotated about the line x equals 4? All right. So x equals 4. I feel like I want to just copy this so I can bring it down to the notes. But x equals 4, positive 4 was it? Yeah, x equals positive 4. That's going to be way over here. So let me see if I can just take a snapshot here. Whoa. Take a snapshot of this. Okay, bring her over here. So we're talking about this line here that's a vertical line right here, right? X equals 4. So it's going to rotate, this way, right? This way, it's going to rotate horizontally around this way. So that's kind of what we're looking for. And of course, we want to take a look at the integral here, y, dy, all that sort of stuff. So what's going to change is that instead of minus 0 here, and we're going to totally rewrite this, so it's going to be the same. This, instead of minus 0, guys, it's going to be minus positive 4. Instead of minus 0, it's going to be minus positive 4. Whoops. I guess the only thing else is that we have to flip around the functions. Okay, so it's not going to be really the same. Let me just rewrite that. So we've got the integral. The integral volume is pi times the integral of. And sorry, I'd like to have all this on the same screen for you, but I don't think I can. So the farthest one away is going to be this y squared. It's going to be y squared minus 4. We're going to square that. And we're going to subtract the inside function, which is the y plus 2. And we're going to minus the axis of rotation there, squared dy. And for this one over here, and I'm going to let you guys work this out, get some practice with your integrals, with your adding in your head without a calculator, please. But I'll set up this integral for you as well. Again, find the volume of the region when it's rotated about the line x equals 7 now, and that's way over here. And that's going to be pretty much the same thing. So volume equals pi times the integral. Oh, I didn't put the limits of integration. Obviously, we're going to go from -1 to 2 here as well. -1 to 2, yeah. -1 to 2. And same thing, y squared, but minus 7 now. All squared minus y plus 2 minus 7, all squared, dy. Okay? So what I want you to do right now is take a few moments, and your turn now to evaluate this on your own. I'll give you the answer in a few minutes, and why don't you try that on your own here now. All right, so hopefully you've all had a chance to get most of that done, at least the first one anyways. So here are the answers for those two volumes. 108 pi over 5 and 243 pi over 5. Those should be the answers that you got. I did confirm one of these with my graphing calculator. I know we don't have calculators on the test for a question like this perhaps, but for the first one, you'll notice that I plugged in the function that's underneath the integral, so the integrand here. Plug that in. I graphed it, and then you'll see I did the integral from -1 to 2. So it filled in this space, and it gave me a number of 21.6. I multiplied that by pi, and I got this decimal, which is roughly equivalent to this exact value. So you see that's the same. Okay, so that's how I checked that on the calculator. And again, there's the answer, and a little bit more work. I didn't, again, show all my steps for sake of space, but that's the answers there for those two examples. So I want to mention too, I don't think I've actually mentioned this in this lesson, but this is also called the washer method. Okay, the washer method. There's two methods. The disk method, which I believe I did mention in our previous lessons. Okay, yeah, disk method here. Okay, and that's where the axis of rotation would be, an axis, and there's no sort of holes that we're drilling out of these solids. There's no gaps. Okay, it's a solid disk. A disk would be, a circle that is completely filled in. Okay, disks, they're solid. Now, what we're looking at here, because we've got two different functions, we're finding an area between two functions, and then we're rotating that area. Because there's two functions involved, this is also called the washer method. Okay, and I'm just going to spend a couple of minutes just explaining that, because I haven't really mentioned this method being the washer method. But this is the washer method in that we have a function minus another function, and we're rotating that area alone. We're not using the solid area underneath or to the left or whatever of one function only. So we're not just looking for this one rotated. That would be the disk method. Solid disks all the way down. You see that? Solid disks. That's the disk method. The washer method leaves some space, some gaps there, okay? And that's what we've been doing this lesson and the last. So I will just zip down to some notes that I have given in the past. Okay, so here we go. So this is the washer method. There's a little graphic that you might find helpful, but I'll just walk through this sort of messy page here. When we're dealing with two functions, we want to rotate a region in between the two functions. The disk method becomes the difference between two solid disks, which is what we've really been fleshing out in this last lesson. So pi r1 squared minus pi r2 squared. The r's are the functions. The far function minus the near function. They're both squared. And we've factored this pi out in front of the integral, okay? So this is another look at it. This is sort of another lesson that I did before. And, we've done pi r squared minus pi r squared, the washer method. This graphic over here might be helpful. A disk is solid, a washer is hollow. It's the difference between two functions. And if we are rotating, around the y-axis, we have to have the function in terms of y, dy, and so on. Okay? So the disk versus the washer method, what we've been learning today is the washer method. You'll see that in your textbooks and different things like that, so please be aware that that's also what this is called. Okay. All right, I'm going to flash some homework up here, but that's the rest of the lesson here for today. Rotation about the y-axis. Please remember that rotation, a normal up-down revolution about the x-axis would be limits are x and x, function is in terms of x, and we've got d of x. And if we're rotating side to side around the y-axis or a x equals whatever line, everything is inverted. Everything is switched. Okay?